In this video, we will implement a very popular Arduino example called knob on a PIC microcontroller. This example allows you to control the position of a servo motor through a potentiometer. The material used in this video will consist of a PIC 16F18855 express board, a Tower Pro SG90 micro servo motor, and the MPLAB X IDE. In most cases, a servo will have a range of motion of 180 degrees. To achieve a specific angle within this range of motion, the servo needs to receive a PWM signal that corresponds to the desired position. Due to the fact that servos have a limited position range, there is a minimum and maximum pulse width that can be accepted. Typically, sending a minimum PWM signal will cause the servo motor to go to the negative 90-degree position, while sending the maximum will cause the servo to go to the positive 90-degree position. Then, of course, sending a signal somewhere in between the minimum and maximum PWM signals will position the servo in another corresponding location. The PWM requirements for a given servo can be found within the servo's datasheet. As mentioned before in this video, I am using a Tower Pro SG90 micro servo motor. I have a copy of this servo's datasheet open. As you can see, this servo requires a PWM signal with a 20 millisecond period. In order to achieve the minimum position of negative 90 degrees, the high pulse of the PWM signal needs to be about 1 millisecond. Additionally, to achieve the maximum position of positive 90 degrees, the high pulse of the PWM needs to be about 2 milliseconds. Now that I have a good understanding of what it takes to make the servo operate properly, I'll go ahead and open MPLAB X and begin setting up my project. In this project, I will be reading analog values from the onboard potentiometer and feeding that value to the PWM to control the servo motor. Therefore, I will start by adding an ADCC peripheral. I do not need to modify any of the settings for the ADCC in this example. Therefore, I'll go to the pin manager and lock the analog input pin of the ADCC to RA4. Pin RA4 is connected to the potentiometer on the express board. Next, I need to go to the pin module and rename this pin to something easier to remember. Once the ADCC is set up, I will add a timer 2 and PWM peripheral to my project. Based on the SG90 datasheet, I need to set up my timer so that it has a period of 20 milliseconds. To do this, I will change my clock source to FOSC divided by 4. Without changing the clock source, the timer will not be able to be used with the PWM peripheral as shown in the notification table. As you can see, currently my timer period is not able to go up to 20 milliseconds. I can adjust this by changing the timer clock prescaler. Now that my period range is able to accept a value of 20 milliseconds, I will enter 20 milliseconds into the timer peripheral field. Next, I will need to adjust my PWM signal to match what is needed to control the servo motor. First, I need to ensure that the PWM is being given the timer 2 peripheral that I just modified. Additionally, I need to find the maximum and minimum duty cycle values that can be used for this servo. Based on the datasheet, to achieve a position of negative 90 degrees, I need to send a 1 millisecond high pulse, which translates into a 5% duty cycle. Additionally, to achieve a positive 90 degree position, I need to send a 2 millisecond high pulse, which translates into a 10% duty cycle. When I set duty cycle to 5% in MCC, it calculates the corresponding PWM duty cycle value, which is 30. Likewise, when I set duty cycle to the maximum, which is 10%, I get a corresponding PWM duty cycle value of 61. These minimum and maximum PWM duty cycle values will be important when I begin coding my project. Lastly, I will navigate to the pin manager and tie the output of the PWM to RC7. This is all of the configuration that I need to do, so I will go ahead and generate my project. Inside of the while loop, I will create a variable called position and set it equal to a single conversion of the potentiometer. Next, I am going to create a map function. This map function is also used in the knob Arduino example. This function takes a starting range of numbers and converts it into a different target range of numbers. In this case, I would like to map the value of 0 to 1023, which will be the outcoming values of the potentiometer, to a range of numbers that match the minimum and maximum duty cycle values, which are 30 to 61. This function will return a 16-bit integer due to the fact that the PWM load duty cycle value function requires a 16-bit input. I will create a 16-bit integer called map value and set it equal to the return value of the map function. I will pass the ADCC position to this function along with the range of the ADCC, which is 0 to 1023. I will also pass it the range of acceptable duty cycle values, which is 30 to 61. I will also need to copy this function definition and paste it before the main loop, or else the compiler will not understand what this new map function is. Lastly, I will call PWM load duty cycle value and pass it the mapped value. This is all of the code that I need to write, so I will go ahead and export my hex file to my express board. As you can see, when I turn the potentiometer, the servo moves as well in the same direction and same speed. In this video, we implemented a very popular beginner Arduino example on a PIC microcontroller. If you enjoyed the content of this video and would like to see more Arduino examples implemented on PIC and AVR microcontrollers, please like the video and comment what content you would like to see in the future.